Hello everybody, I'm back again with another video. This is actually an important one. We're on chemical equilibrium. This is finding equilibrium concentrations, and I added end partial pressures. The section in the notes just called finding equilibrium concentrations. You can definitely extend the ideas to pressures as well, partial pressures of gas phase species. This is a huge skill. This skill will carry over for a big chunk of the course. We'll use it all the time. If you go on to chemistry, you can use these type of calculations all the time. You better believe if you're going on to take the chemical GRE or going to med school or things like that in the future, you will see problems that entail elements of this. So the goal here is we have a certain amount of information, and it will vary, and we'll talk about those cases, and we need to find the equilibrium concentrations or partial pressures. I might eventually just say concentrations, but I'm implying both. Basically, you're being able to figure out what the composition of that system will be when the system comes to equilibrium, given enough initial information. You have to be provided with a proper amount of info. This in the note set, which I actually have in some of the notes. This is in the unworked out note set. It's approximately about page 17, and I say that because, as I modify these things, the page sometimes shifts by a page or two. So the section will be called Finding Equilibrium Concentrations. The simplest case 1, I call it in the notes, is when you're missing the concentration or pressure of one species, one chemical species. You know everything else, you know all the other concentrations, and you know the equilibrium constant K as well. So that's direct to solve. If you see something like this is a no-brainer to solve, let's just work one out. This is from the notes. Let's say you have the reaction we did before, SO2, Cl2 gas in equilibrium with SO2 gas and Cl2 gas. And we're told at a certain temperature, I said, let's see here, at a certain temperature, this is here at 227 degrees Celsius, K, what is it, Kc in this case, is 2.99, and actually Kc, well no, they will be different. Kc and Kp will be different. 2.99 times 10 to the minus 7 is given, and we have some information on this system. We know that the SO2 concentration, and this is written in the notes, is 4.00 times 10 to the minus 7 molar. We know that the SO2Cl2, the concentration of this is at 1.00 times 10 to the minus 2. All that's molar. And the system is at equilibrium. That's a key thing. The system is at equilibrium. At equilibrium, what will be the concentration of Cl2? This is really simple. You just write Kc is equal to 2.99 times 10 to the minus 7. And then that's equal to the products, which is going to be, we're doing in molar concentrations, SO2, Cl2, both to raise their first power, meaning you don't have to write anything. SO2Cl2 in the denominator, products over reactants. There's only gases here. And we put in some values. This is, so mathematically, this is 2.99 times 10 to the minus 7 is equal to SO2 concentration. That's 4.00 times 10 to the minus 7. I'm not going to write units in because the units will ultimately come out to be molarity for this. By convention, these don't carry units. There's no units built into Kc, so it's a little deceptive. You say, well, the units cancel here and cancel here. There's no units. It's the anomaly associated with defining Kc dimensionless, but at the end we'll pick up units for Cl2. We have that, and then we have what do we have here? SO2Cl2, that's 1.00 times 10 to the minus 7. I have to erase a little bit up top here. So all you do is you solve. It's going to be Cl2 concentration is going to be 2.99 times 10 to the minus 7 times 1.00 times 10 to the minus 7 divided by 4.00 times 10 to the minus 7. A lot of 10 to the minus 7s here. And so what do we come out with here? Let's see here. We have 2 times, oh, I wrote that down wrong. This is 10 to the minus 2. I thought there was too many. 10 to the minus 2, there we go. I thought there was too many 10 to the minus 7s. As I was saying this, I got carried away with that. So we change that down here. That's 10 to the minus 2. So you get a good look at that. We'll change it in situ here. And then so you solve for this, and this will be, I came out with 7.48 times 10 to the minus 3 molar. So that's it. So when you do this again, because of the convention that Kc is not carrying units, we still at the end will assign the concentration of the species in units of molarity. Just self-consistently plug in molarities for the other reactant species and solve it algebraically directly. Basically cross multiply the 10 to the minus 2 and divide by the 4 times 10 to the minus 7. Check the numbers. But that's the simplest case. It doesn't get simpler than that. The second type is definitely highly testable, and I'll just erase the board with my soccer race here, and we'll go over that. So as described in the notes, we'll call this case 2, and we'll do a couple different variations of this as we go along. So this is finding equilibrium constants when K and the initial concentrations are given. So we have okay, so we have K, and now we have the initial concentrations. Before, we had 2 of the 3 equilibrium concentrations. These are initial concentrations, and unless perchance we just happen to set it up with an equilibrium composition at first, which is exceedingly hard to do, in general not going to be at equilibrium. If we're sitting to the right or to the left of it or at equilibrium, we're going to determine that. This is a method commonly called ICE method, but I'm going to call it the DICE method. And the reason why is because we really want to figure out the direction the reaction goes before we do anything mathematically further. And that's not emphasized enough. Now this problem, I call this a canned problem. This is like the books always have this problem, and I'm certainly going to give you one because you might see one on an MCAT or future test, but it's a misleading problem if it's the only one you do, because let's first write the equation out. So we have an equation. This would be roughly on page 18. A pretty simple looking reaction. CO, that's not cobalt, that's a capital O. Cl2 gas going to carbon monoxide gas and Cl2 gas. That's the reaction system. That's what happens at equilibrium. We have some data on it. We know at 500 degrees Celsius, the equilibrium constant, we're doing this in terms of Kp, so this will be pressure. Kp is 0.304. That's given to us. And all we know is that this system starts out with 0.500 atmospheres of this carbon, I forgot what that's called, that's carbon dichloride, something like that, but COCl2, and none of this and none of this. The system can't be at equilibrium. It doesn't have any of the products. So if you wanted to write here, if you wanted to do that and say Q sub P is equal to products, we'll do this with pressures. This would be the partial pressure of carbon monoxide, partial pressure Cl2, divided by the partial pressure ClCl2, and that's going to be 0 times 0 over 0.500, which is a big old 0. 0 is definitively less than any K value we'll have, because K cannot be a negative number. So the system is without a doubt going to head to the right. Now you sit there and say, yeah, it's a no-brainer. It has no products, we're going to head to the right. And very often the books present that as like the problem. That is one of many problems. Typically, let's take biochemistry. You're observing a cell in situ, and you do measurements of the composition of the material, the cellular material that's in the cell, associated with a particular reaction, all the substances that are associated with it. You may be at equilibrium, or maybe the systems is such that what you're measuring is not at equilibrium. You could be before it, the back of it. You might have all the components present and be at a position at equilibrium to the right of it or the left of it. And you can certainly set up a reaction system where it's got a mixture of 3 different gases mixed together, and it goes either to the right or the left, or it's in the rare case when it's equilibrium. But to set something up, say, okay, we always set an experiment up where there's only the reactant, no products, that's a very misleading thing. And a lot of books will put 3 or 4 problems like that before they get to something else. So this problem, this should not be a one and done. You have to do other types of problems to get this. So that's the dice, is the direction. The direction for this is that Q is equal to 0. There's no partial pressures of the gases that are the products, and we have a finite number, a number not equal to 0, I should say, for the COCl2. The reaction is heading to the right, so it goes to the right, or arrow to the right. This allows us to set up the algebra. Now, you can do different methods here. They call this the ice table, so we put the concentration labels on top. You can do something like that, so we could put pressure of Cl2. This is all going to be in atmospheres. I'm not going to keep writing that over. You put it right on top, and that's going to be, we'll make like an initial amount, right? We'll have like initial, this is 0.500 atmospheres, and then the pressure of the, what do we have? I want to follow the same order here. The carbon monoxide is 0. The pressure of the Cl2 is a big old 0. So that's your I of the ice, right? And then the change, this is where people tend to make mistakes. Is like they forget, like, I don't know what goes positive, negative. Well, you're going to the right? You're going that way. So what's going to happen? That's a minus x, right? You're losing this, and then it's 1-to-1 stoichiometry. And again, that's another trap, is people stop at that one problem that's a 1-to-1 stoichiometry, which is a good place to start. When you lose one of these, you gain one of these and gain one of these. So this is a plus x and a plus x. That's the change part. This is just a way of succinctly doing the algebra. There's nothing magic about this. In the old days, we didn't do it this way. So we just did it for brute force algebra, just setting it up using algebraic logic. This is a table method. I actually think it's pretty good. And then the equilibrium part is, I just say bring it on down. 0.500 minus x, x, and x. It's kind of boring, but that works. So now, using this framework here, except for Kp, Kp is the same thing. It's the partial pressure of CO, the partial pressure of Cl2, partial pressure of COCl2. Plug in here identical to what these represent by in terms of x's and numbers plus or minus x. So this is going to be x times x is going to give us x squared. And then we're going to have in the denominator 0.500 minus x. And that's going to be equal to 0.304. Guess what? That's a quadratic equation. That's a quadratic equation. If at this point you say, holy crap, I haven't studied the quadratic equation in years or forgot it, go back to the math primer and review that. I have some purely mathematical examples. So I have to erase some of this. We can rewrite it down. So you want to get a good look at this frame here. I'll stand back. You can blow it up and write things down. I will put the solutions for this in the worked out note sets. There'll be a version of this worked out already. So we'll go on. We have all this, you have it written on a piece of paper, or you can go back and look at the footage, because this will take a board or two to work out. I was going to flip the board around and have it continue on, but there's too much potential for calamity. I got a frying pan right here by me that could go flying off. So we have the algebra set up. I'll just write it again. We have 0.304 equals x squared 0.500 minus x. Now you're basically setting it up. Get it to the point on your own where you have x squared, you cross multiply, you multiply through by the 0.304 for this term, x squared, we'll write it as a linear equation, 0.304x minus 0.152 is equal to 0. Get to that point right there and you'll be in good shape. We, of course, are cross-multiplying it, multiplying through, and then I'm putting it all on one side so the signs change, right? So the positive just number you have here becomes negative, and the number with the negative 0.304 becomes positive when you bring it over. No magic there. That's a quadratic equation. That's a quadratic equation. And it is a quadratic equation where I'm not going to make any approximations to solve. I'm going to solve it directly. If you have a solver on your calculator, you're welcome to do it that way. There's going to be two roots. I'm going to call it x1 and 2. And they're going to be in the form of minus b plus or minus b squared minus 4ac all over 2a. That's the coefficients here. A is equal to 1. There's a 1 in front of that. B is equal to 0.304. That's the coefficient in front of the linear x term. And then C is just the number, negative 0.152. Negative 0.152, right? So we have that. Now we just plug it on in. So we have, for B, we have minus 0.304. It's a minus b on the outside, so we change the sign there. Plus or minus, we have two roots, two solutions, if you will. B squared is 0.304. I'll just put a bracket around it to be clear. A minus, but the C is a minus, the A is a positive, so this will be a plus, and that will be 4 times 0.152. We don't have to write the 1 in, that's just kind of redundant. So we have this term, it's had to change sign because the minus times the minus, and then over 2, A is 1. So we have two roots. Go through it, and the two roots that I get, I'm going to keep a couple extra sig figs on here. I'll say x1, I'll just give them different names. I'm having extra sig figs on here just to do out the math. 2, can't do this in my head, of course. I'm looking at my worked out solutions. 6645 ATM. And then we have x is equal to negative 0.57045 ATM. This is the real root. This is the, I shouldn't say real because you might think real number. This is the root that we're looking for because we want to be subtracting off the minus x off the COCL2. So let's go back to the table. All we need is the roots right now. So those are the partial pressures. And think about what the x's represent. A lot of people stop the problem here, and that is not the solution of what we're looking for, at least wholly. Remember, at equilibrium, on the ice table, on that last step, for the PCOCl2, we have the form of 0.500, and that's actually atmospheres minus x, and then the PCO and the PCl2 at the equilibrium, the E step, we have an x and an x. Well, that means the interpretation of that is the partial pressure of CO is equal to partial pressure of Cl2, and that's precisely this value. I'll write it to 3 sig figs, 66 ATM. And then we have, beyond that, let's see here, we have here the partial pressure of the COCl2 is going to be 0.500 minus, and that will be in ATMs, minus this number here, 0.26645, right? And so we have that, and this gives me, what's it give me here? It's always hard to see these things when I'm looking at the little tape. 0.234. That's great. So that's the answers. Now, here's a key step. It's ice, it's dice, but there should be a final step. Check your answer. Check your answer. You know what K is, so you should be able to see what K does wrong. I'm going to plug these in with some more sig figs to be as close as possible. This answer is only good realistically to about 3 sig figs, but let's do it out with more sig figs just to see how close we can get. So I plugged in like 5, let's say. So for the in the numerator, we have 0.266, and again, I added a few sig figs from my calculator, squared, and then in the denominator, we have 0.23355. Oh, forgot that. 23355, so forth. It's not squared, and when I do that out, I got 0.304. Now, if you do this out, you get 0.30. 35 or 0.30 45 or something like that. I mean, it's just a rounding issue somewhere here. But if you ended up with 5 or 17 or 10 to the minus 7 or something like that, then you clearly made a mistake. So go back, but you can always check to see if your answer, I'm not going to guarantee it's correct like that, but you'll know if it's wrong. Okay, so you'll definitely know if you've made a significant error if you don't come out with anything that's within a couple percent of what you'd expect. Again, don't be retentive about it. Don't sit there and say, "Oh wow, I'm off by 0.5%." You have multiple mathematical steps here where you did rounding potentially, and I do them realistically on my calculator, holding as many sig figs as I can. So that's a good example. We'll do some more with some different conditions. You definitely, rework this problem, see if I made any minor typos or errors in there. Let me know if I have. I'll put it in the description if I have, unless it's something real big, then I redo the video typically, but I haven't found anything like that. Work as many problems you can. I have made not only a skill builder on equilibrium, but there's also one on the ice, or if you want to call it the dice method, because I would always check the direction of the reaction first. This case was trivial. It had to go to the right. There were no products to start out. But in a lot of cases, it's not. And people always like, oh, they always go to the right. No, they don't. Sometimes they go to the left. Sometimes they don't go anywhere. That's a rarer case. So on that note, I may have time to make another video, maybe not. I hope you enjoyed the video, and take care.